Now, another term we have to know about the mechanical property of the material is known as the hardness of the material. Now, in real life, we know that we have two terms. We are either going to have a hard surface, for example, and soft surface. We can have a hard person and soft person. So opposite to hard is soft. So just a very simple example, if I'm going to talk about the rubber, is soft material. If I'm going to talk about the steel, is hard material. Now simply how can we check the hardness of the material? So first we have to know what the definition of the hardness. The hardness is the resistance to the permanent indentations. And the good hardness usually is going to mean that the material is resistant to the scratching and the wear. And most of the tooling used in manufacturing must be hard for the scratch and the wear resistance. Now when we talk about the tool, for example, the cutting tools. So the cutting tool should be hard enough to do cutting but not getting wear very fast. So we have something called the hardness test, which is commonly used for assessing the material properties because they are quick and convenient. We have two types of the hardness test. The first one is known as the Brinell hardness test, and the other one is the Rockwell hardness test. The Brinell hardness test is the oldest, and the Rockwell is the newest one. I cannot say, well, it's not new because it's appeared in the 21st century. Actually, everything we're talking about came from the late 19th century and the early of the 20th century. So the Brinell test, we are going to have a hard wall, which is going to press into the specimen surface with different loads. We start with 500, then 1,100 or 3,000 kilograms. And the diameter usually of the ball is going to be about 10 millimeter diameter for the indenter, made of the steel, or in the new days they start to use the cemented carbide material. So what's happening is we're going to press the force. We know what the diameter of the intender ball, with a certain force on the material is going to be indenting a hole in it. Actually not hole. It's going to copy the shape until it's going to stop at a certain value. We can take the diameter of the shape of the indentations, and we can find the relationship between these two values to find what is the hardness of the material according to the Brinell hardness test. You can search about this one. I'll just give you a general relationship between the the general procedure of the measurements of the specimen hardness. On the other side, Rockwell decided instead of using the ball shape, he decided to use a wedge shape. Okay, so he started to have a cone shape indenter instead of the ball shape indenter, and the testing is going to be on two stages. In the first stage, they're just adding initial minor load of 10 kilogram. So under the 10 kilogram, we measure what the depth we are going to have for the indenter in the specimen. Then we are going to increase the load to the major load of, for example, 150 kilogram. It's going to be higher, and we are going to find the value of the indentation after the adding of the major load. Find the value D, which is the difference, and from this value we can find what is the Rockwell test value. Now, it's very important to know what's the effect on the temperature on the mechanical properties of the material. Everybody knows how the blacksmith is working, for example. You know that he's heating the part before he starts to do the work on it, before he's going to do actually the forging on it. And what's happening is that if I'm going to add a temperature to the material, I'm going to heat up the material, you can see that the tensile strength is going to dramatically decrease, the top curve. The yield strength also is going to decrease. When these values are going to decrease at elevated temperature, that means I can reach the yield strength and passing the elastic region to the plastic region in lower value of forces. On the other side, I can see that the ductility of the material or the percentage of elongation will dramatically going to increase. That means if I'm going to heat up the metal part, for example, that means I'm going to need a less force to cause the permanent deformation on the part. And this is a very important thing in manufacturing. On the other side, if I'm going to work as a hardness of the material, the temperature elevation was simply going to reduce the hardness of the material. So this makes the material softer, and this will make it much easier to form. Okay, so the hot hardness is the ability of the material to retain the hardness at elevated temperature. So you can see that the most affected one is going to be the low carbon steel, and followed by the high alloy steel, while the ceramic is going to be the less, and then followed by the highest carbon steel. Now we talked about the recrystallization in the metal. So the definition of that, if the metal is going to be heated to a sufficiently high temperature and then deformed, the strain hardening does not occur. That means it's not going to have a higher stress to do the forming of the metal. Instead, new grains are going to form and are free of strain, and the metal has recrystallized. The metal behaves as a perfectly plastic materials if the value of the N is equal to 0, and then the equation of the stress, which is equal to the K multiplied by the strain up to power N, will be simply reduced. The stress is going to be equal to the K value. Now we had to reach a certain temperature, which is known as the recrystallization temperature, to have this effect. And you know that recrystallization is going to take some time until we're going to reach this temperature, and the recrystallization temperature is specified as the temperature at which the new grains are going to be formed in about 1 hour. And the recrystallization temperature of the given metal usually is going to be equal to 0.5 Tm, where Tm is the melting point in degree Kelvin of the material. The application of the recrystallization in manufacturing, the heating of the metal to its crystallization temperature prior to the formation allows the greater amount of the straining, and then thus we are going to have lower forces and power, as we said, are going to be required to perform the process. And forming and metal at a temperature above the recrystallization temperature is going to be called the hot working. Okay, so hot working example once again is the blacksmith work, forging process, or what we call the hot working forging, or whatever the thing is. That's it for today's lecture, and hope to see you in the class next week. If you have any question, you can come back to me by sending me an email. Thank you very much.